Tess is all about looking for planets like Earth that are revolving around stars outside of our solar system. And so, I think when I went to college down here in Melbourne, Florida, a long time ago, there were no such things as planets around other stars. Nobody had ever found one. So that field has come a long way. Kepler really opened up the field a lot, found thousands of planets outside the solar system, but many of them are too far away for scientists to do additional research of, because it's interesting to find a planet around another star, but boy, wouldn't you like to know, could life exist on that planet?
So we're looking for life in other planets.
That's really, and you got to do it step by step, right? So Tess by itself can't find life on other planets, but we can find planets that are orbiting around stars in orbits that could support liquid water as one indication of the potential for life. And they are rocky planets. They are more Earth-like planets. They're smaller planets. So given those indications from Tess, now telescopes like James Webb could go off and do much more extensive research to look at the atmospheres. They have those big, powerful mirrors that we don't have. They can look at the atmospheres of those planets, because as they fly in front of the star, the light coming from the star goes through the atmosphere. And if you have a really big mirror now, you can capture the light as it got attenuated through the atmosphere, and you can say, hey, is there carbon dioxide? Is there nitrogen? What kind of gases make up that atmosphere? Another clue about life. And then you build yourself even a bigger telescope, and you could actually take a picture. So slowly you're getting there.
It sounds like Tess is doing a survey of the sky,
right,
of the entire sky, looking for planets that might be habitable, that either that Webb or other kinds of telescopes could look for. But what about ground-based telescopes? Will they be able to investigate some of these planets as well?
Yeah, and in fact, what Tess is as a project is not only a telescope in the sky. We have ground-based observatories supporting us as well. Because when you do transit science, is what we do, all you can see is that a planet went in front of the star and blocked out a little bit of the light. So all you can tell is how big is the planet volume-wise compared to the star that it went in front of.
Right.
You don't know how heavy it is.
Okay.
So you don't know the density. You don't know if it's rocky or watery or gassy.
Right.
So you have to use ground-based observatories that could do a different type of science. What they do is they look at how the planets tug at the star. So the gravity of the star is pulling the planets to keep them in orbit, but those planets, even if they're small, are tugging at the star, making it wobble a little bit. And that little wobble can show up. From ground-based observatories, they can see that wobble to tell how massive those planets are. We tell how big they are volumetrically. Ground-based observations tell you how heavy they are. Then you get the density, and you can tell, are they a water world, a gas world? So all these things have to fit together, and it turns out that from space, you can't do a good job at finding the mass of a planet. You could do the photometry really good in space. So we're focused on what's best to be done in space. Photometry where you don't have to look through the sky, you're looking from space straight out to the star, so you can count every photon arriving. And what's best to be done on Earth, we leave it to the Earth base.
Okay, great. So let's talk a little bit about the satellite itself. So could you describe roughly how large is it?
Yeah, it's only about 5 feet high. It's only about 700 pounds. We have about 100 pounds of fuel on board at launch.
Okay.
And so that sounds awfully small compared to like James Webb or something.
Sure.
But it is extremely powerful. So what's special about Tess is the cameras that are on board, right? So those cameras have some of the best CCDs that have ever been made, extremely sensitive, so they'll help us count photons arriving from stars, looking for transits of Earth-sized planets where there's only a small change in that photon output. And we've got these really complex lens systems that have a large field of view vision, but allow that light to all be concentrated on the CCDs.
So it's going to be launched into orbit, as I understand it, with a Falcon 9 rocket.
Yep.
So would you describe a little bit about the orbit that this satellite is going to go into?
Sure. So on launch day, what you'll see here is we'll launch out of Cape Canaveral here, launch into low Earth orbit, and then the second stage will relight on the Falcon rocket, and it'll shoot us out towards the moon. We'll be out over Africa at that point. So they'll shoot us out towards the moon, and then over the next 2 months, we'll do a number of burns of our own propulsion system, put ourselves into a big elliptical orbit that goes outside of the geo orbit when you're down towards Earth. So it's still pretty far away from Earth. And then you swing around out to lunar orbit, not when the moon is there, but then you go out to that distance, 250,000 miles or so, and then swing back towards Earth. So every 2.5 weeks, we swing by Earth. we dump data to the ground, and then we circle back out again 2.5 weeks, and we stare at the sky looking for exoplanets. We do that for 2 years.
Now, what happens after 2 years? Is it going to fall out of orbit or what?
Now, so officially we designed it to last at least 2 years. We have enough fuel to go much longer than that, so we could go for decades. If somebody will continue to fund the project, we'll continue to fly. We could stare at different parts of the sky for longer periods. We could do all kinds of different activities.
And can you tell us roughly what the cost of this mission is?
From building the satellite and getting it ready, our life cycle cost for the whole satellite and all of the stuff we're doing on the project, it's about $240 million.
Okay. Thank you for being with us today. This is Jim Siegel signing off from the Kennedy Space Center.